I am currently working on a top-down shooter game inspired by math and geometry. In this game you shoot points, cast rays, and launch circles to kill polygons, destroy pyramids, and even fight the platonic solids. Instead of using a tile map to design the levels, I decided to use simple shapes such as lines, polygons, and circles that work as the level's walls and obstacles. I even created an in-game editor to create the levels. Since my game is about math, I wanted it to have a style similar to those oscilloscope animations and retrofuturistic vector graphics I have seen in educational math videos. I also want to render simple 3D shapes, such as spheres and cubes. There is one problem though. I am working with a 2D engine. The game engine I'm using has no concept of the Z-axis, as it was designed to develop games that require 2D graphics, mainly using sprites and tiles. However, even the most advanced 3D engine still renders its world on the same flat screen a 2D engine does. There is nothing stopping me from drawing 3D shapes on a 2D game. I will have to do some extra coding to create the illusion of the third dimension. Through this video, I will guide you through the math needed to turn a game that looks like this into this. The way we convert a game's world to a flat surface is to use a projection, which is a function that converts a point in 3D space to a point in 2D space, which can then be drawn to the screen. Points, lines, and polygons defined in 3D space turn into shapes drawn in 2 dimensions. There are many ways of doing this. We can simply ignore the Z-axis and map the X and Y coordinates in 3D to the plane. Essentially, we will flatten the entire game world into an infinitely thin slice. The projection would look like this: a function that takes the X, Y, and Z coordinates and returns a 2D vector. We use this projection function on every point to draw the world. For example, the 2 endpoints of a line or the vertices of a polygon. This looks okay, but we lose information about the Z-axis. It is very hard to distinguish two objects that share the same XY coordinates. The isometric projection is a good way to convey a sense of depth. It is used in many games and in mechanical and architectural drawings. This projection makes the 3 orthogonal axes, X, Y, and Z, have the same length, hence the name isometric. This is very useful when measuring objects in the field of engineering. We first rotate one axis 45 degrees, and then rotate around a different one to make them all appear to have the same length. By choosing the correct matrix and angle, we can rotate a point in the X, Y, or Z axis. For an isometric view, there are 8 possible orientations, depending into which octant the viewer looks. Rotating a point can be done using matrix multiplication. Note that, unlike multiplication of numbers, the order in which the matrices are multiplied will affect the final result. The game now looks sort of 3D, but there is one thing missing. Things that are further away do not look smaller, and things closer to the viewer do not appear larger. This is because we are working with an orthographic projection, which means that the projection lines are always perpendicular to the projection plane. No matter how close or far the object is, they will appear to be the same size on the screen. In real life, the effect of perspective creates vanishing points, where parallel lines appear to converge at infinity. To fix this, we need to add a focal point, like the one found in any real-life camera. All the light rays pass through this point and then hit the projection plane. This way, the size of objects will depend on the distance to the projection plane. Additionally, we can change the focal length to adjust how much perspective affects the vanishing points. For example, an infinite focal length will essentially become an orthographic projection, as the light rays become parallel to each other. Using geometry and similar triangles, the Y and Z coordinates of a point can be scaled depending on the distance to the focal point placed on the X-axis. This will apply the effect of perspective as if we were looking directly into the X-axis, with the screen centered at the origin. In my game, after rotating the camera to get an isometric view, I placed the focal point on the Z-axis, which created the following projection. Notice that now the function also depends on the focal length, which in combination with the Z coordinate will scale the X and Y components of every point. Another subtle effect is introduced with shaders. I added a bloom filter to the bright parts of the image, and I also blurred the top and bottom parts of the screen to simulate the tilt shift effect. Blurring is done using the box blur, which is a very simple kernel that produces a really convincing blur. For the bloom effect that gives lines that glowing appearance, a Gaussian blur is used, which requires extra computation. This enhances the illusion of depth by making close and far objects appear out of focus, similar to a camera with a very narrow depth of field. This method is not perfect. This works well for drawing simple shapes, but more complex objects require work that's beyond the scope of this video and my programming abilities. For example, all the objects are sorted every frame, so things that are closer to the screen are drawn last. This rudimentary 3D engine cannot handle shadows, object intersections, and a lot more. But for my game, it works more than fine. After all this, you may think that I could just have used a 3D engine instead of wasting time coding this, and you are right. If your goal is to make a 3D game, I would recommend you use an engine that was made for that. But there's no harm in learning how the fundamentals of computer graphics work and how math is used to accomplish this. You can try the free demo of my game on Steam and join the Discord server to get more updates. Thank you.